This conference will now be recorded.
Very good evening, friends. Today we'll be completing this electromagnetic induction chapter by discussing grouping of inductances and few numerical problems from IIT JEE papers. Okay, so let us first discuss about the grouping of inductances. So grouping or combination, you can say grouping or combination. So combination, as you know, combination in case of resistor, we have seen combinations. We have seen combination in case of capacitors. Okay, so here we are seeing combination of inductors, right? Inductors, and you know, inductors have, see, if I use inductors, see, in case of resistors, there are two types of combinations. One is series combination, another one is parallel combination. So here also we'll see similar type of combinations or grouping of inductors, series combination or series combination and parallel combination. But here in series combination there are two things actually. Since these are coil, see I have this one. Okay, see here there are two coils of the two inductor coils. See, first one, if I say the inductance of the first coil is L1 and inductance of the second coil is L2, and they have mutual coupling constant, like mutual coupling, coefficient of mutual coupling, that is M. And see now the series combination results in two different effect actually. Okay, they can be connected in such a way that the current in both the coils will be flowing in the same direction. As you see here, see from here the current is flowing, and see we are assuming that the inductor coils are coiled or wound in the same sense, so that we are taking by default as an assumption that both the coils are wound in the same orientation. It is not like this. Okay, it is not like this or something like this. So it is wounded like the coil is in the same sense. Okay, both are coiled in the same sense, and they can be connected in both ways actually. In two ways they can be connected. In one way, here we are seeing the inductor coils are connected in such a way that the current in both is flowing in the same sense. You look this, see current goes from here all the way, then goes through the coil, and then it comes out like this, and see it goes like this, and again here coil like this, and comes out like this. So that means, you know, here the current is flowing in the same sense. So this is one type of series combination. So in this type of series combination, what happens, see obviously, you know, this coil will produce a separate EMF, let us say E1, and this will induce some other EMF, that is E2. So induced EMF due to both the coil will be different, even though the current is same, because in self inductance is different. Okay, see L1 is different than L2. All right, and also they are connected in the potential or EMF up to this is E1, and up to this will be E2. All right, So both are actually producing induced EMF E1 and E2. Now, since in both cases, first of all, the coils are like inductors are coiled in the same sense. Second thing is that the current is flowing in the same sense in both cases. Current is flowing in the same sense. So what will happen, in this combination, the EMF, induced EMF gets added up. So in this case, induced EMF that is E induced or E equivalent I can write. So that will be actually added up. That means I will get induced EMF will be added up. EMFs will be added up. Since current in the both coil is flowing in the same direction, that is the reason. That means what we are getting, E equivalent is equal to E1 plus E2. Okay, this is the thing. Now what is E1 and what is E2? See, since both the coil through the both coil current is flowing in the same, like current flowing is the same. So E1, see, self-inductance will actually produce some self-induced EMF, that is L1 di dt. So self-induction, okay, or self-induced EMF due to the current change in the same coil, and mutual inductance here will be minus M di dt. Since current is flowing in the same sense, the mutual inductance also will be in the same sense. Induction produced, induced EMF produced due to mutual um, coupling. See here, actually this M is the coefficient of mutual coupling, but this current is actually changing. See, this factor is actually due to the second coil. Okay, we know always that induced EMF, like EMF induced in a coil when the current is varying or magnetic field is varying in the other coil. So that's why this change in the current, since the same current is flowing, so these two are same, but basically we'll see later that this is the current. So this is the factor which is related to the coil 2. Okay, similarly here E2 will be minus L2 di dt and minus M di dt. Okay, so these are things. Now I have to use this. So if I do this, you know what we get? Minus, let us take minus common. So L1 plus L2 plus 2M, okay, plus 2M into di dt. Okay, so this is what we get. Now look, if I replace these two inductor coils with a single coil which has which is capable of producing same induced EMF. Okay, same induced EMF. Suppose I take a coil having, okay, instead of taking two coils, I take a coil which has in self-induced like self-induction. I'm sorry, in the self-inductance E equivalent, which is capable of producing the same EMF. Okay, then what we can write in this case? If I just replace these two coils with a single coil, so we'll get E equivalent is equal to minus L equivalent. That means what? I am just replacing two coils with a single inductor coil which has equivalent self-inductance Leq. Then it will be Leq di dt. Okay. So if I compare these two equations, equation 1 and equation 2, this is actually with really using two inductor coils having self-inductances L1 and L2, mutual inductance between them or mutual coupling between them is M. But instead of using these two coils, I can use only a single coil. Okay, only single coil which has equivalent self-inductance Leq and which is capable of producing the same induced EMF. Okay, so now comparing 1 and 2, comparing equations 1 and 2, what we get? We get L equivalent is equal to L1 plus L2 plus 2M. Okay, L1 plus L2 plus 2M, that is actually the equivalent self-inductance. Okay, equivalent self-inductance. So here, what is the bottom point, or what is the take-home message from here? The take-home message is that if we have two different inductor coil, okay, and if we connect them in series such that the current is flowing in the same direction in both the coil, so in that case the combination would give an equivalent self-inductance, that is L equivalent is equal to L1 plus L2 plus 2M. Okay, where M is the coefficient of mutual coupling or mutual inductance. Okay, so this is one important result we have learned. See, if there is no mutual coupling between these two, then what will happen? This M will be 0. In that case, it will be L1 plus L2. That means this gives actually the real series combination of resistance. In case of resistance and parallel combination of capacitor, we know the equivalent capacitance is L1 plus L2, or in case of resistor, it is actually series combination of resistors. Okay, L1 plus L2 here. If M is 0, that means there is no mutual coupling between them, between the coil inductors. Then it will be L1 plus L2. Okay, L1 plus L2, just like resistance. Okay, so just like resistance, R equivalent is equal to R1 plus R2. This is in series, right? So similar to that, L equivalent is equal to L1 plus L2 plus 2M. And when the mutual coupling is not there, then this term goes, so you get L1 plus L2 is equal to equivalent self-inductance. Okay, now we'll just move on to another combination, that is actually, this is also series combination, but you look here excuse me, here the coils, inductor coils are connected in such a way that the current in both will not be in the same sense. See the inductors are coiled in the same sense, that is there, but they have been connected in such a way that the current in both the coil will be flowing in the opposite direction. So the connection has been made in such a way that the current in both the coil will be in different directions. Like say in this case it is in this direction, and in this coil it is this direction. So in such case, what will happen? You know, the induced EMF will be like here. See, flux linked itself will be getting subtracted. The flux which will be linked in this type of combination will be actually subtracted. Okay, flux linked will be subtracted, and hence the induced EMF also. Okay, so see in this case what we can write? We can write, see, this is E1 producing E1, this produces self, so like induced EMF E2. So this E1 could be written as minus L1 di dt. Okay, this is due to the self inductance. Due to mutual coupling, you know what will happen in this case. See, this is minus m. See, this is actually d I2 by dt, and I2 is in which direction? Opposite to this. That's why this term will be positive, because the current here, this is L1. Oh, sorry. Well, anyway, this is I and minus I. Okay, I1 means I and I2 means minus I. Okay, so this current is same, but current is in the opposite direction. That's why this particular term will be positive. In case of C2 also, sorry, omega 2 also, so this will be minus L2 dt, sorry, di by dt. And here it will be di dt. Okay, so if we take this, now I have to simplify this and to get the equivalent EMF. So in this case, what will be the thing here? You know, if it will be, if I say it is added up, because I have already considered the sign over here. Let me take this code getting added up. So this will be minus minus 2m L sorry di by dt. Okay, so now if I just replace this whole like this combination of this inductor, okay, combination of this inductor, so this will be actually L eq. Okay, L eq, that means, you know, equivalent inductance. So that will be here actually L1 plus L2 L1 plus L2 minus 2m. So students, we can see there are two types of series combinations of inductors. In one case, what happens? The same current is flowing in the same direction, but in this case, same current is flowing but in the opposite direction. So that's why there is a modification over here in the mutual inductance part. Okay, so we'll just go to the next part. Okay, so now we'll see if the inductor coils are connected in parallel, what happens in that case? What will be the equivalent inductance of the combination? So in this case also, the parallel combination or parallel connection can be made in two ways. One is shown here. The inductor coils are connected in such a way that the current in both is flowing in the same direction. Okay, as you see in the figure. So in this conductors, the current is flowing in the opposite right direction. This also is flowing in the rightwards direction. Okay, so these are the inductor coils connected in the connected in a manner such that both the inductor are carrying current in the same direction. So look, then in this case what will happen, just like parallel combination of resistor, we know that since both the ends are same, connected to the same place, this this are at the same end, so the induced EMF or induced EMF in both the coil will be the same. So they induce same EMF. Okay, okay, so in this case, look what will happen. Since the current is flowing in the same sense, and also they are connected at the same ends, then EMF induced will be the same. So we can write for both. Then okay, so this is one thing. So in this case, what will happen if we write this? Actually, these are all same. Okay, now if we simplify this, what we are going to get? Okay, so if we solve this for L equivalent, you know what we are going to get. So L equivalent will be in this case. So actually where we were saying what will happen. So equivalent inductance will be, sorry, just a minute. So in this case it will be, sorry, L equivalent. L equivalent will be L1 L2 plus, sorry, L1 L2 minus M square. Sorry. Okay, this is actually equivalent inductance for parallel combination with current in the same direction. Okay. In the second case, in this case, you know the current direction is different. Okay. Current direction is different. This you can see the orientation is different. That's why current direction is different. So for current direction also, current direction different. In that case, you know what will happen? The equivalent inductance will be L1 L2 minus M square. Okay, so these are actually two things here. Actually, this is not 4. This is L1 L2. Okay, so this is for parallel combination. The same story in this case also. Okay, so this is with combination of uh, inductor coil. Now we'll just learn about AD currents. So we have seen induced EMF is produced in case of coil, etc. Okay, circular coil or any conducting coil. But you know, the induced EMF can be produced or can be induced. Induced EMF can be produced or may be produced, sorry, may be produced. Induced EMF may be or can be produced by a metal sheet or metal or bulk or within the bulk of the metal. Okay, or within the bulk of the metal. Okay, see, I have got a figure for you, representative figure. Generally, what is eddy current? You know, when you have a conducting material inside a varying magnetic field, in that case the flux linked within the see, within each layer of this bulk of the conducting material, each layer there will be change in the flux, and that change in the flux will actually produce induced EMF, and that EMF, in this case the EMF is actually in the opposite direction. I'm sorry, in the opposite direction, in the sense, what I try to say is that uh, within the bulk of the metal, when the magnetic flux changes, there will be induced EMF, and that will actually form a circulating current. Okay, AD current means what? AD current means circulating current. AD current means circulating current. Circulating current, and this circulating current actually will be in the plane, circulate current in the plane perpendicular to the magnetic field. So what is eddy current? Within the bulk of a metal, when there is a change in the flux, magnetic flux, so induced EMF will be produced, and that EMF will produce that induced EMF will actually produce circulating current, as you see, and this looks like the wirelings of eddies. Okay, wirelings of eddies, and these circulating currents actually will be confined in a plane perpendicular to the magnetic field. So this is eddy current. See, eddy current is not very much desirable to arise in our useful experimental or application setups, like in the motor or in the core of the transformer. We use bulk material, right, as core. Okay, or in case of motor we use the core as soft iron or something like that. So we shouldn't use in a bulk. Okay, we should not use that in bulk. Otherwise, what will happen? This eddy current will be induced in the bulk, within the bulk of the metal, and this eddy current will actually produce lot of heating effect, and that will actually burn out the electric insulation of the windings of the coil or windings of the, like, it will remove the, like, it will, yes, it will actually spoil the insulation. Okay, insulation of the conducting wires in electromagnets or in the transformer, etc. So it actually produces a lot of heating effect, and to save the whole instrument from this enormous heating effect, there should be chilling units, and to run the chilling unit, you need to use power, right? Electrical power separately. So it actually, eddy current causes, indirectly or directly causes loss of energy, loss of energy. Causes loss of energy indirectly. Now see, these are the disadvantages. Eddy current induced within the iron core of the armature of electrical motors, dynamos, within the cores of the transformer, which produces an unnecessary heating effect, which is wastage of power. The heat produced by the eddy current may damage the insulations of the coil also. That is what I was saying. Now see, since this is this, like, these are the disadvantages of eddy current, at least in case of dynamo, electrical motors, etc. So we need to actually, even if we use, see how to, we have to use the armature, we have to use the core materials within the electromagnet, right, or in the motors. We cannot avoid that. But what are the ways to minimize the eddy current effect? So one way is shown here. So instead of using the whole bulk material, see, this is the bulk material, we can use laminated. See, I can just cut it down to very, see, equivalent or like identical plates, or thin identical plates. Okay, kind of that we can make, and then we can stuck them. We can, like, we can stuck them together with insulating glue. Okay, such that they look like this. See, these are actually one sheet. Instead of using the whole bulk metal, we are using sheets made of that particular material, and they have been actually glued. Insulating glue has been used to stack. Okay, when you do that, what happens? Look, in case of bulk, see, the circles are how big they are. That means they are actually producing lot of eddy currents and lot of heating effects. And see, throughout, see, they have the exposure to the whole area. But in this case, look, in this case, see, eddy current always passes in a closed path or produces a closed path. Eddy currents flow laminated core. See, this is actually a laminated core. Laminated core, in the sense, core material material is cut into thin slice. Okay, those slices are stuck together with insulating glue, and this as a whole will act as an armature or core material. So in this case, you know, even if the circulating eddy current is produced, look, in each case, since these are nearby, but there is insulation in between them, so the current cannot grow within this whole region of these two. Okay, they will be confined in a narrow area. Okay, narrow area, one point. Second point is that, see, when it goes like this and come back, the direction at this particular position, the direction of the eddy currents will be just exactly opposite, and magnitude anyway becomes same. So equivalent magnitude, this is going, this is coming out. So due to this, you know, the net current will be, due to this, the net eddy current will actually be zero, because they will add up to zero. See, this goes like this and this goes like this, so they will cancel each other. They will cancel each other. So these two currents will cancel each other, and another layers will do the same, and then it goes on. Okay, so here the heating effect is less, and also there will be no addition of current. Like addition of current in the sense there is no eddy current. Actually, they will see, as I said, the direction of the current in the consecutive layers will be different, so that they will cancel each other. Okay, one lamina, eddy current in one lamina will cancel that eddy current in the other lamina. So this is what happens. Okay, and this is the way laminated, using laminated core materials, this effect of eddy current can be minimized. Now, what are the disadvantages? Sorry, what are the good applications of this inductor coils? Sorry, this eddy currents. So eddy currents has disadvantages, but at the same time it has a lot of applications also. See, we know now, we are all familiar with the induction furnace. Actually, heating effect, you see, heating effect of heating effect of eddy current. Heating effect of eddy current is being used here. Is being used here in the induction furnace. See, electromagnetic damping, to see, if I have two electromagnet, suppose this is N, this is S, kind of that. Okay, S. Now, if you have a very thin metal, if you have a thin, suppose metallic, so suppose this is a metal sheet or some metal plate, small plate, which is actually capable of oscillating uh, across this region. Okay, across the region, that means it can go out and in this region. Okay, now when when the switch on, the electromagnetic switch on, you know what will happen? This will eventually start this will actually eventually this the motion of this actually will be damped. Okay, motion of this will be damped. It will not move in the region here. Okay, so that is actually electromagnetic damping generally in dead bit. It is used in dead bit galvanometer. Dead bit galvanometer. Galvanometer. Dead bit galvanometer. Okay, dead bit, not moving coil. You should not forget with this. Okay, dead bit galvanometer. So this electromagnetic damping is being used in dead bit galvanometer. And one among all the uses, the famous like most famous use is the use of this eddy current is the electric brakes in the train. Okay, electric brakes in the train. So there is a drum, right? So in that, what happens? How we can explain that? So in train, eddy current is set up in the drum attached to the wheel of the train. See, in the with the wheel of the trains, there will be some drum attached. In that drum, actually, what will happen? The eddy currents will produce due to the, see, we have used the metallic rails, right? In there, actually, eddy current in gets induced, and that eddy current will be actually damping the motion of the train. Electric. So there may be many other applications of this eddy current. Okay, so thus we have completed the theory part of this chapter. Now we can solve one or two problems, numerical problems from previous year JEE advanced paper. I'll just solve one problem on electromagnetic induction part. Okay, from electromagnetic induction part, let me just write the question. This is actually from JEE advanced 2013. Let me write JEE advanced 2013 paper. The question says the change in magnetic dipole moment associated with the orbit okay, I'm sorry, there is, I think, linked question. Okay, so yeah, it is actually related to atomic magnetism. Atomic magnetism. Let us just write this part. I'll just read you the paragraph in short for you. So this we have to find out at the end of the time interval of magnetic field change is, there are few options here, whether minus gamma b q r square. Option B says minus gamma b q r square by 2. Option C says gamma bqr square by 2, and option D says it is gamma bq r square. So let me just read the paragraph for you in short. So there is a point charge q which is moving in a circular orbit of radius r. Okay, suppose this is the case. So there is a charge q which is, this is a positive charge which is moving in a circular orbit. Circular orbit, this orbit in actually in xy plane with angular velocity omega. Okay, charge is moving. This can be considered as an equivalent current carrying loop, and where steady current is q omega by 2 pi. This is the current flowing in this particular loop. A uniform magnetic field along the positive x-axis is now switched on. So, positive z-axis. So this is in the xy plane. This is x. Suppose this is y, xy plane. This is, and now magnetic field is actually placed in the positive z direction, and that, see, b changed from 0 to b like this. No, 0 to b. So that's how in a second. That's how there is a change in the magnetic field. Assume that the radius of the orbit remains constant. The application of the magnetic field induces an EMF. The application of the magnetic field induces an EMF in the orbit. The induced EMF is defined as the work done by the induced electric field in moving a unit positive charge around the closed loop. It is known that for an orbiting charge, the magnetic dipole moment is proportional to the angular momentum. Magnetic dipole moment, okay, so magnetic dipole moment mu is actually proportional to the angular momentum. Okay, I into A, right? I is q omega by 2 pi, A is pi r square. Okay, pi r square. Now see, pi goes off, what we get? Q omega r square. So if we want to make, see, q by 2m, let me write q by 2m, and this is m omega r square. So you know L will be mvr, and v is equal to r omega. So that means here this will be q by 2m, m, r, and omega will give you v is equal to r omega. Okay, from this one r I'll take, so that will give you v, and this r, mvr. That means you know the q by 2m into L. This is L, angular momentum, And in case of hydrogen Bohr orbit, for a first Bohr orbit, this is actually EH cross. Okay, I'm sorry, this is H cross. Okay, L is equal to NH cross, so L is equal to H cross for first Bohr orbit. If we use that, you know what we get? Q by 2m E H cross. Sorry, not E. I'm just writing wrong. So NH cross for the first, N is 1. N is equal to 1 for first Bohr orbit. So EH by 2m. EH by 2m, this is actually magnetic moment for first Bohr orbit. And this is actually denoted by mu b, Bohr magneton. Okay, this is how it is related. Now the question actually, uh, the question is that we have to find out the change in the magnetic dipole moment. The change in the magnetic dipole moment. Okay, so that is what we have to find out. So dear students, so how to solve this change in the magnetic dipole moment? See, magnetic field is in the perpendicular direction to this particular loop, right? Loop. Let us say current is flowing in this direction. Or let us just take in another way. Current is flowing in the clockwise direction and magnetic field is out of the plane, So induced EMF will produce a current, right? Produce a current in such that will oppose this magnetic field. Okay. So what is delta L? Delta L can be written as tau. See, we know L is equal to dl by dt is equal to torque. We know that, right? So from there we can write this as this. Now what is torque in terms of magnetic moment and all? Okay, so how to write that? What was the information given? Information was given is that current was given, right? Current was given and we could find out magnetic field from magnetic moment from there. So here actually from here, say tau could be written in terms of the question says the magnetic dipole moment associated with the orbit. So this torque is QE into R, okay, into delta T. R is the radius of this. This is Q, and for here, see, this is actually EMF induced in that. Okay. We know this will be actually BR into R, and change in 1 second. Okay, delta T is 1 second. So this will be actually QBR square by 2. And we know delta M, change in the magnetic moment, is actually R into delta L. We have found out the delta L. I'm sorry, this is gamma, not R, gamma. So gamma into QB R square by 2. Okay, so this is actually the magnitude of the change in the magnetic moment. But you know, the angular momentum and magnetic moment, we know that angular momentum, if it is this way, and magnetic moment will be in this way. So they are opposite to each other. So that's why we can write this as minus gamma q b r square by 2. Okay, so this will be actually the answer. That means this is B. The answer will be B. All right, so with this we'll stop it here for today. We'll be discussing numerical problems in the latest series of the lectures. Now what we are doing, we are just covering up the critical concepts of various chapters. So next chapters we will be learning alternating current, LR, LCR, CR, LC combinations, etc. Okay, and transient phenomena in charging capacitor or in the inductor, how current grows, current dies out. So those things we'll be learning in the next class. Okay, so thank you for your patience. Bye for today.